many H's do you have coming off? And how many S's? And you said 12 electrons. So if we put in 12 electrons, 2 and 4, and remember, what about H for today? Okay, 2. No dots, no extra lines, so those are covered. So 6, 8, 10, 12. Check to see if everybody has its 8. The H's are good. C has 8. S has how many? Is it happy? So what are we going to do? We're going to take 2 from the C and put them where? On the S. So what geometry would this be? How many are on the C? 3. And how many lone pairs? So 3 and 0, I heard it already. Triangular planar. All right. Now, what can you tell me about all 3 bonds? Are they the same or different? So as long as those bonds are different, this is automatically what kind of molecule? Polar. You don't even have to ask yourself if it has lone pairs because it automatically defaults for number 1. So it's a polar molecule. Everybody good with that one? Okay. Number 2. ASBR3 had how many electrons? 26. All right, so 26. AS is the central atom. 3 BRs. And my electrons are the wrong color. All right, 26 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, once I draw in my 26 electrons, does everybody have its 8? Yes. So how many atoms do I have sticking off? And how many lone pairs? 3 and 1 makes the geometry triangular pyramidal. All right, and polar or non-polar? It's polar. Has a lone pair. All right, and the last one was CI4. All right, CI4 has, C is the central atom. How many I's? 4. How many electrons am I putting in? I'm putting in 32. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everybody have 8? How many atoms do I have? How many lone pairs? So it's tetrahedral. And tetrahedral tells us what? Non-polar. So all the bonds are the same, and there's no lone pairs. Question about the lone pairs. Feel okay about it? Those are the 3 things you're going to be asked to on the quiz. All right, let me find the homework real quick. Now, I did not pull the homework up, or do the homework in chart form, I should say, but it's done in columns like the homework. Now, there's a couple exceptions on this homework that I'll have to explain. All right. Now, clearly this is column 1. This is the molecule with the geometry, and this is the far column. Now, one of the exceptions is here. And there's another one on the back side. Okay. Now, check and I'll explain. That way. All right. So why is it an exception? It does have a lone pair. All right. So everybody always says this has a lone pair, so this should be polar as soon as they see the lone pair. What'd you get when you subtracted 2.1 and 2.1? You got 0. So when you subtract 2.1 and 2.1 and you get 0, it has no dipole. Okay? In order to be polar over here, you have to have a dipole. You have to have some electronegativity difference. Okay? You have to have at least a 0.1. Because there is no dipole, because there is a 0 when you subtract, you can't be polar if the difference is what? 0. So if you get 0 on everything, do these lone pairs matter? No. Okay? That's why it's non-polar. Very, very, very seldom are you going to wind up with 0 when you have a lone pair. So 9 times out of 10, when you look and you see a lone pair and you go, oh, lone pair is polar, you're fine. But if you got 0 on all the bonds, it's going to be a non-polar molecule. Okay? It can't be polar if the difference is 0. Does that make sense? Okay. All right, next set of answers. Other than that weird one, are we getting the answers right? Good. All right, can I put the next set up? Okay. Ready for me to move on? Cut. Last one. Now, this one, same thing. When you subtract, you got 0 there. Now, those are nitpicky exceptions. Have I done that to you on the quiz? What? No. I have not found nitpicky exceptions on the quiz. Guys, I promise. I'm looking for overall general understanding. I'm not looking for nitpicky exceptions to throw you off. Again, that one equals 0 to subtract, which is why questions that in economics. So we're good, we understand, we can draw those structures, we know geometry, as soon as we memorize the chart, and we tell the polar not polar. Okay. Now, you need a periodic table. If you would like to use your electronegativity table so that you've got the electronegativity numbers, then by all means use that. If you don't care about the electronegativity numbers, and you just want to bring one because you just need the column to know how many outer shell electrons, then use that. If you want both of them, then you may have both of them. You just can't have notes or color coded periodic tables. Okay? Let's go with it. You can borrow one of mine. You can only use your electronegativity table. your name on it, and then draw your structures and label your information for them. kill them. All right, that's first the front. Alright, so we got to finish up what I would call some delivery department. So, we're going to talk about onyx bonding and how we represent it first. And then we have to talk about the properties and differences between onyx, metallic, and galvanic. Hopefully we can get all that done today. And then we'll only have one small piece possibly to do tomorrow. That way we can spend the rest of tomorrow reviewing these tests on Monday. I really don't want to push the test Tuesday because I am almost positive Tuesday's push that. Let me double check, but I'm pretty sure I'm right about that. Tuesday. 21st. Tuesday. That's what day Tuesday. I'm pretty sure I will, brother. And given this is, I think, the longest test we take, I don't want to push it to Tuesday because I have a couple of people in first period who struggle to finish, as it is. So we can't do it in less time. And the stuff that we have left to do tomorrow would be very, very small. So it wouldn't be a big deal to have to pick that up tomorrow. There's one free response question, and there might be one multiple choice question. So it's very small. All right, so we're going to finish with onyx bonding and start with onyx bonding, and then we'll talk properties. Now, how is onyx bonding different from covalent bonding? Everything you just did on today's quiz was covalent bonding. So when you drew those glue structures, you were showing what? Okay, so what's the key word I wanted you to remember? Covalent bonding is about, okay, shared electrons. When you did the geometries, you were talking about shared electrons. When you talked about polar molecules and non-polar molecules, you were talking about shared electrons, right? Now, when we talk about ionic bonding, what are the key words for ionic bonding? Okay, so what are the words that go with that other than not sharing? Electrons are this or that. You might want to know that for the test Monday. You will see it somewhere in multiple choice. Guaranteed. There you go. Okay, electrons are lost or gained. That would have been the right answer. You should have gone with that. All right, so electrons are lost or gained in ionic bonding. So, since the electrons are lost or gained, we want to demonstrate that in an ionic structure. We cannot show that with a Lewis structure because the line shows sharing. So, we represent these more as a balanced equation. Okay? So, let's say that we want to show something like, and I'm going to do a really easy one that everybody can relate to, like salt. Okay? NaCl is the traditional ionic compound everybody can associate with. So, the way that we show that is in the form of a balanced equation. So, we write it like Na plus Cl there. Now, on this side, you show where the electrons are originally. Okay? You show where the electrons are originally. So, what do we know? You don't hear that. You don't. Oh, that's cold in here. Well, I'm having a bad, I'll be warm. I'm going to be right. So, what do we know about sodium? What did I just write down there? Show where the electrons are originally, right? So what do we know about those electrons originally? What am I asking you to draw? If we're talking about where the electrons are originally, that we might already know how to do. Isabel's pulled over there. She pulled up around here. Not by myself. So what do we know about electrons originally? What do you think I'm referring to when I say that? Actually, what am I talking about? You remember? Okay, so what would we have drawn using the periodic table a couple weeks ago? What was the circle called? That's what I thought you were talking about. No, not a Bohr diagram. You're in the right time period, though. We've been after a Bohr diagram. John? No, what did we learn to draw using the periodic table? They showed where electrons are. Okay, we showed the outer shell electrons. Those are what we're talking about. What shows the outer shell electrons? Depending on the group. It had a name. Start with a D. Ah, what was that? There we go. All right. You're going to show a dot diagram. So, sodium has a dot diagram of how many dots? 1. How do we know that back there, Alexis? It's in the first group, so it's got 1 dot. Okay? So, what kind of dot diagram would chlorine have? Have 7. How did you know that? Group 17. Everybody remember doing that? Okay, so that tells us where they are originally. Now, based on what we've learned this semester, we know that sodium is going to do what with those electrons? Okay, this is not lose or gain. What will sodium definitely do based on what it has up there? It will lose. What will chlorine definitely do? It will definitely gain. Okay, so on this side over here, we're going to show where the electrons go. Because we know what's going to happen. We know sodium's going to lose an electron, and we know chlorine's going to gain the electron, right? We know this. We know sodium has 1 in the outer shell. We know chlorine has 7. We know all atoms will have how many? 8. We drew Bohr diagrams. We showed how sodium could lose 1. We showed how chlorine could gain 1. We know that's going to happen. So that's what we're going to show in the equation. So, over here, we're going to write Na plus Bl, and we want to show that sodium lost it and chlorine gained it. So, if sodium lost an electron, how am I going to show it lost 1 electron? You what? Okay. So, do not draw electrons. Okay? The sodium, we're not going to draw any electrons. What else are we going to do to show that it lost an electron that we've learned this semester? Okay? We're going to add the electron to chlorine, which means we're going to draw dots on chlorine. So, we had 7. Now we have 8. Okay? We're almost there. We need the one other thing that we know how to do that we've learned this semester to show that somebody lost and somebody gained. What do you think it is I want you to remember? And yeah. So who gets the plus 1? What? So Na lost 1 electron, so we get the plus 1. And chlorine gets a minus 1 because it gained 1. The last thing we would need to do would be to balance it if it was not balanced. But what do we know about this equation? already balanced. Got one Na, one Na, one Cl, one Cl. So it's already balanced. Okay? Are y'all with me? Okay. I'll make it work this way. All right, so let's say we have Mg plus F. Okay? How many electrons does Mg have? Okay? How many does F have? Okay? All right, Mg is going to do what? Lose 2. So, where are they going? F can only take how many? So, one was there, I still got one. So what's the charge on the Mg? Plus 2. Because we lost 2. Fluorine gained how many? But I still got this one with electrons. That's the question. So we get it back to Mg, so Mg only loses 1. But if Mg only loses 1, will it have its magic number of 8 in the outer shell? No. So will it be happy if it still has 1 in its outer shell? No. It won't be happy. It's got to lose both of them, right? So fluorine can only take 1 of them. So how on earth are we going to be happy if we only have 1? Can we just cast this one off into space and say, be gone with you? Can we do that? No. It'd be really cool because if we could, I could get rid of my cat. But can't do that either. So we'll never forgive me. That's for my husband Woody. Much as I'd like to do that cat. All right. Now, I'm going to add something. If I add magnesium, what's magnesium going to do? All right. What's magnesium going to do? It's going to do what? What did it do over here? So I would wind up with how many electrons it needed at home? So will that help? Yes or no? No. So what if I added a fluorine? What if I added a fluorine? Would that help me? Well, fluorine has what? It has 7 electrons, right? It needs what to be happy? It needs 1 more electron. Could it take an electron like this homeless little electron there? Yeah. So this one could just slide right in there and become the 8th electron that's homeless. Okay? So when you lose 2 from magnesium, and only 1 could go here, you have to add something. Now, you can't just pick a random element. You can only either add a magnesium or add a fluorine. Well, magnesium was going to do what? What did it do on this side? Lose. So when I tried to add a magnesium here, what was it going to do? Lose. So I wound up with how many electrons it needed at home? 3. Did I want 3 electrons that needed a home? No, because I already had 1 that needed a home. 3 wasn't going to help me. So I added a fluorine. Fluorine had how many? It had 7. So when I added 1 more gave me my magic number of 1. Gave me 8. So now I just put in my minus 1. Is my equation balanced? No, because I have how many F's on this side? So I put 1 here. Voila. Question. Now, what if I have 1 like this? I have K plus O. How many electrons does K have in its outer shell? Okay. How many does O have? All right. What is K going going to do with its one? What is O going to do? Now, O only has how many? It only has 6. Is it okay with only having 6 electrons? Sorry, 7 electrons. No. It only has 7. Now, happy with 7. It wants how many? It wants 8 like every other atom will take, right? So, we have to add something to this side in order to get the magic number of 8. Now, if we did like this one, and we added an O, like we added a negative F, O has how many electrons on? 6. Is that going to help us gain anything there? No, because O doesn't lose anything, right? So who could lose electrons and donate to our O? K loses electrons and can give to our O. So K will lose and give one there. So now O has what oxidation number? -2, because it gained 2. It gained 1 from K and another one from K. K has a +1. That K has a +1. Now, is the equation balanced? We got to put a 2 in front of the K. Think you can try one? Okay. Y'all do FR plus CL and do those two real quick. who wants to put SR plus CL on the board? Go ahead.
Yes.
Good job. Anybody have a question about that? Everybody okay with that? All right. So these will all be response questions. Next. Anybody? Volunteers? Gregor? No. Somebody else. I realize we only have 9 people, but come on. Good. Now, the only thing I want to talk about is the dot diagram on the plane option. Now, I would not take off for Agilent and Agilent 6 dots, okay? Most of you probably drew the same 6 dots as you drew. Anybody draw it different? Okay. Now, let's say, because we're tested on the periodic table on Monday also, right? Let's say I said draw the dot diagram for oxygen. Is this the dot diagram for oxygen? Or not? Let me draw the dot diagram for oxygen. All right, oxygen has a configuration of He, 2s2, 2p4. So when you draw it, 2s is paired, 2p4 has 3 singles, and then it pairs up, right? So when you actually draw this, are all of these pairs? No. You have 2 pairs, a single, and a single. Okay? So in something like this, I wouldn't take off for 2, 2, and 2. But if I just said in a question, draw the dot diagram for oxygen, I would expect you to be able to do this to draw the dot diagram for oxygen. Okay? You see the difference? Because we've learned how to do this, I would expect you to still be able to do that. Everybody good with that? Okay. Now, we're going to talk about the properties of metallic, really focus color, like Judas Brown, onyx, and covalent bonds. Now, I'm going to make a table to do this. And because I'm going to put so much stuff in the table, I typically use one board for each column of the table. So I'm not sure how y'all want to do this in your notes. So I'll let y'all decide that. Some people use the whole page and turn it sideways. Some people just follow along, but I'm going to bounce between boards. Covalent will be the smallest column with the least amount of space. Some people just write and then add the next column or the next section, but because I'm going to start here and then go to here, and then I'll go back, okay? Some folks don't leave enough space and then they get mad at me. I'm just warning you ahead of time, okay? So we're going to start with metallic bond. And then I'm going to do onyx. And as I compare them, I'm going to bounce between them. Covalent will have the absolute least stuff because I will have the least to say about a covalent bond. Okay? Now, a metallic bond. How is metallic different from ionic and covalent? I told you, first of all, that this is the definition that was the weirdest when we defined it a little over, I guess it was close to a week ago now. Okay? Electrons are donated to a region in space. It's referred to as the electron feed model. Now, the reason we call it that is because the electrons are not attached to any one atom in the metal. They're freely moving. So, if I draw, I'm not an art maker, so you have to bear with me. If I draw a representation of a piece of the metal, okay, the positives are representing the nucleus, and the E's are going to represent the electron. Okay? Yeah. Now, in the metal, these electrons can go wherever it is they wish to go. They are not locked into place. They can travel throughout the metal. Okay? These electrons are freely moving and mobile, which is why we call them a sea of electrons. Now, how does that compare with other bonds? Okay? Are other bonds able to move in this fashion? Are other, like onyx bonds, are they able to do this, for example? Onyx bonds able to move? No, they're not. Right? What's my battery stand? That's not bad. I mean, look. All right, everybody caught up with me? All right, so an onyx bond. How is an onyx bond different? Okay, I'll come back to my conductivity test for a minute. I don't think I'm on 9 volt. All right, an onyx bond. All right, we already said the electrons are lost or gained. Now, these electrons are locked into solid crystal. about salt. Most of you can visualize the salt you used on your food last night at dinner, perhaps. Okay? Ionic bonds tend to be crystals, just like the salt you use. Now, because of that, they are in, the electrons are locked into position in a crystal lattice. Now, you really have to work with my artistic license here, because you thought my metal looked bad, and we see nothing yet. All right, there are 7 crystal structures. I'm not going to make you memorize the names or use them, but there are 7 structures. Okay, they're like hexagonal, orthorhombic, cubic, triclinic, things of that nature. I'm not going to make you memorize what they are. I'd struggle to come up with all 7 myself. Now, let me draw something in a different color here. All right, let's just say that this is our crystal structure. Now, I'm just trying to draw something that's sort of diamond shaped, but I can't draw 3-dimensionally. So my diamond shape looks terrible, so I don't want to do that. But, you know, I'm art teacher. I can't draw. Yeah. Okay. This would be my crystal lattice. Okay. Now, this, if I just colored in down here, would be my unit cell. I'm sure I'm not skipping anything important. I don't think I have so far. Look at all that. Yeah. All right, so what is the unit cell going to show us? Okay. The unit cell is the smallest crystal that shows us the height of crystal pattern or structure. Okay? For example, NaCl is cubic. So if we saw 1 grain of salt and it was cubic, what would we know about all the other grains of salt? They would all be the same. 1 unit cell of salt is cubic. All the other crystals of salt would be cubic. All right, ice is hexagonal, and I will teach you this when we study solids, liquids, and gases also, because this is not all this stuff. Ice is hexagonal, and we'll talk about what happens with ice and why it's hexagonal down the road, okay? But if ice is hexagonal, and that freezes in a hexagonal pattern, once 1 crystal forms in this hexagonal, what do all the crystals do? They're all going to be what pattern? They're all going to be what in A? They're all going to be hexagonal, okay? Snowflakes are different, but they have different patterns, but if you could break it down into the individual unit cells, all of the unit cells would be what shape? They'd be hexagonal because all snowflakes are made of what? Ice or water. Yes. Okay? Now, What is a crystal lattice then? A crystal lattice is just an orderly arrangement of crystals. Okay? And that can be as many crystals as you want, depending on how big it is. If you had a giant chunk of marble, it would be millions of crystals. But the unit cell tells you the structure of whatever crystal you have. Now, there are only 7 crystal structures. Now, how do the properties between an ionic bond and a metallic bond differ then based on those two structures? What properties do metals have now that ionic compounds don't have? Tell me what you remember about metals. What properties do metals have? They what? Okay, the electrons move freely, so what things do metals do that ionic compounds don't do? Think middle school, think earth science, think some other science class other than mine that we talked about that metals have, that are properties of metals. I teach this in physical science all the time. What? They are solids, both of them are solids. But I'll put that up here, okay? These are solids too, just like ionic are, except Hg. Mercury is the only one that is not a solid. Let's see. Yeah. Except Mercury. They're going to be solids except for Mercury. But ionic compounds are solids too, so that's not hugely different. And it's not really about the electrons. What properties did y'all learn about metals in middle school? What do all metals do? Should you put them in an electrical socket? Why not? They what? Yeah, they'll shock the snot out of you. Okay? They are good conductors of heat and electricity. Okay, they are good conductors of heat and electricity. Okay, why? Those electrons are able to move. Those electrons are what carry the current. When you stick a fork in the outlet, those electrons flow through the fork and up your arm to zap you. Okay, if the electrons couldn't move, could the electrons flow up your arm and zap you? No. Okay. Number 2. What else do metals have? They are malleable. They can be rolled into sheets. Why can metals be rolled into sheets? I can beat on them with a hammer all day long because what do those electrons do when I hit them? They move around. Metals are ductile. They can be drawn into a wire. So I can squeeze them tight into a wire. Because when I squeeze them into a wire, what do those electrons do? They just move out of the way. They're like Play-Doh. And the other one you need to know is metals are lustrous. What does lustrous mean? Shiny. My God, y'all's middle school education sucks. That is like straight middle school. All right. Now, this one's high school. Metals are the strongest bond, which means they have the highest melting point and boiling point. This will be important for our discussion in the morning. Guys, they have the highest melting point and boiling point. Afternoon. Right, y'all will be back in the afternoon tomorrow. Okay? So that's the piece we'll need to do tomorrow at start of class. They have the highest melting point and boiling point. Okay? They have the highest, strongest bond, highest melting point and boiling point. Now, how does this compare? If I got it, we're going to need to wait. All right, so how does that compare to ionic bonds, where everything's locked into place? Electrons can't move. So, can we conduct if you can't move? No. Okay? You cannot conduct electricity. Why can't we conduct electricity? The electrons can't move. Okay? The electrons cannot move, which is why I wanted my battery to work, so I can show that to you. My battery is, whoop. In a second, I'll see if I can get some salt out before we press that. All right? Can I hammer it? Can I hammer a crystal and make it flat? No. What happens to it? It breaks apart. Ionic compounds are brittle. Okay? They're brittle. Everybody knows that breaks easily, right? Okay? So, if they break easily, they're not malleable nor ductile. And they're not lustrous. Okay? They are strong bonds. They have high melting points. Now, are they as strong as metallic? No. They're not as strong as metallic. Now, from there, where does that leave poor old Cobain? Leaves them sort of dead last. Okay? Everybody got what they need? Got it. Now wait on it. Okay? So, the last type of bond is covalent. And we know from our discussion the last 2 days that the electrons are shared, right? Now, these are, first of all, the weakest bonds. The electrons are locked into place. So, if I tell you those two things, if they're the weakest bond, what does that tell you about their melting point and boiling point? It's very low, okay? Very low melting point and boiling point. Okay? Very low melting point and boiling point. If the electrons are locked into place, all right? If the electrons are locked into place, can we conduct? No. Okay? Cannot conduct electricity. Okay? Cannot conduct electricity. Can we be malleable or ductile? Nope. Not malleable or ductile. Now, this category, because it has such a low melting point and boiling point, has many liquids. Okay? So, here's a new vocabulary for you. It's volatile. Okay? Because there's so many in this category that are liquids. These are volatile. Volatile means you evaporate easily. Now, you y'all ever put alcohol on your skin? How long does it take to dry? like seconds. That's volatile. If you ever use fingernail polish remover on your hands, okay, you get fingernail polish remover off, and there's some of the guys probably have it, but if you've had sisters who've ever tried to paint fingernails, maybe you have. Okay? So, if you've ever had that experience with a fingernail polish remover on something to get it off, fingernail polish remover dries incredibly easily. That's volatile. Okay? Question. Next, the only thing I want to ask you is, can I make covalent or ionic conduct? Can either of those be made to conduct? Nope, not if you mix it with a metal ore. One of them can be, and you're on the right track with mixing it. Not covalent. Ionic can be made to conduct. So how can we make ionic conduct? Two ways. How can I make an ionic compound conduct? Now remember, let me go back to metal. I'll flip back there. What made a metal conduct? What allowed metals to conduct? The electrons are moving freely, right? That's all you got to have are moving electrons. So why won't ionic compounds conduct? Okay, so in order to make them conduct, they got to be able to do what? So how can I make them move? Huh? How can I get them to play? Without smashing. I just get them to move. How can I get them to move easily? All right. So heat doesn't know what's going to do to it. So guess what? What am I going to do? Nothing. All right. Melt or liquefy them as one. Which is often referred to as molten, because they were a crystal, and so once a crystal is liquefied, we call them molten. Now, I do not have anything hot enough in here to molten them, okay? But there's something we can do very easily. Very easily. Do the same thing. Make the electrons move. What? No electricity. It might hurt if I start throwing crystals at people. Easier than that. I'd be willing to bet you most of you did this summer. Nope. Went swimming. Okay? Now, all that chlorine this summer went in the swimming pool. If there's an electrical storm, thunderstorm, whatever, and you're in a pool, what do you have to do? Get out. Because if lightning strikes the swimming pool, you're dead. Okay? All those chlorine atoms. Okay? If you think about it, let's just talk about a regular old beaker. You got some salt in here. You put NaCl, not even high potency chlorine from the swimming pool. But you got some sodium ions and some chlorine ions, because you just put some salt water in here to gargle with because you went to the dentist. They're all floating around in there, right? Those are your moving electrons. If you put an electrical current in there, it's going to carry electricity. That's just a little bit of ion. Imagine a giant swimming pool. Have y'all ever seen how much chlorine gets dumped in there? People pee in that water. Not supposed to pee in a swimming pool. Okay, but people do. If you don't think so, ask the people who are on the swim team what they do when they practice for swim meets, or when they swim, when they go swim practice. Ask them how many of them pee in the swimming pool. Do they get out of the swimming pool when they practice, or they pee in the swimming pool. You will be appalled to find out how many of your classmates pee in the swimming pool. I was appalled when I asked with you. Okay? Several years ago, I taught a Chem 2 class. Almost everybody in my Chem 2 class was on the swim team. I taught Cole Reagan. I don't know if y'all remember him. He was a senior. He got a swimming scholarship. He still swims, I think, today in college. Anyway, he spent 3 to 4 hours every day in the pool. Swam for High Point swim team there, swam for us. He swam 3 hours a day, every day. He said, well, I can't get on to this. He said, I'll be in the pool. I'm like Michael Phelps. I'm Michael Phelps. He gets out, he's in the pool. Or pees in the pool. Michael Phelps, he's in the pool. Okay? Now, I find it all rather disgusting. Not sure I'm ever going to a place like one I get the pool ever again in my lifetime. Okay? But lots of people do. So we dump lots of chlorine in the pool. Those are dissolved ions. Those ions are moving electrons. Any kind of electrical current that runs through that carries that electrical current directly to any kind of body that's in the water. It will electrify and vacuum. Now, can that be done in a covalent bond? No. There are no ions here at all. So can we make a covalent bond conduct? No. The only one that can conduct is ionic. You can make it conduct, but it doesn't conduct on its own. You don't have to worry about your lunch salt. That. Okay? Now, the only thing we have left to do will be van der Waals forces with boiling point. Now, based on what we did today, let's say I ask this test question. All right, well, I hand out the homework paper. Let's see if you can answer this. All right, so what you come up with out of the question on the board? All right, I hear Effie. Agree, disagree, discuss, what we think? You should agree, okay? Now, based on the discussion we just had, you need to look at bond type, right? So, what can you tell me about NaCl? It's what kind of bond? Who? Well, that's what you said. All right, NaCl is an ionic bond. CCl4 is covalent. Ki is, and Fe is metallic. Now, based on our discussion about properties, who was the strongest bond? Metallic was the strongest, then ionic, and then who? Covalent. So, if metallic was the strongest, it had the highest boiling point, and this one had the lowest boiling point. That's what you should have gotten out of what we just talked about. That was the conclusion you should have drawn. Okay? Did you? Yay or nay? Did I completely botch that when we were talking? Or did you get there on your own? Some head nodding, thumbs up. No, Ms. Wall, something would be very helpful here. Yes, I got thumbs up. Patrick's nodding at me. Yes, Angela's nodding. Brandon, you with me or no? Okay, so because of that, that means that iron would be the one with the higher boiling point. Everybody there? Okay, now we have one little more piece to do with that tomorrow, and then we're done and ready to test. Okay, but we're almost there. It'll probably take 20 minutes to do the last piece we've got to do. All right, now, let me shut that off.